Assalamu alaikum. So we are discussing the lecture 3 at the minute, and in this lecture we are at uh, so we have discussed couple of problems along with the different inversions for 4-bar mechanisms. So currently we are at the inversions of double slider crank chain basically. So in our last lectures, we have solved one of the example 5.4, which was about Whiteforce quick return mechanism. So the next is basically the double slider crank now. We had a brief overview already, so I will just go through again. So a kinematic chain which consists of two turning pairs and two sliding pairs. So we got two turning and two sliding pairs in this double slider crank mechanism. Uh, this is called as a double slider crank chain as shown. So we see that the link 2, which is basically one of this one, link 2. This is the link 2 and link 1 form one turning pair. Link 2 and link 1. So link 1 is basically this cylinder B. So this one along this one, so it's making turning, so that's why it's a turning pair. And link 2 and link 3 form the second turning pair. So link 2 and link 3 is, this is another second turning pair. Turning pair means it has some angular movement basically. Let's say it's alpha. Link 3 and link 4, the link 3 and link 4 is basically slotted plate. So this all slotted plate is just one link because this is fixed. So this is link 4. So link 3 and link 4 are making a sliding pair. So it's moving that way. So that's why it's a sliding pair. So this is one of the sliding pair. And of course, this is link 1 and 4. This is another sliding pair basically. Right. So within this, we have this called as elliptical trammels. So this is quite outdated equipment, but it was quite interesting mechanism. So that's why you see this mechanism still discussed in many of different textbooks for mechanics of machine. So it is an instrument used for drawing ellipses. So you can draw ellipse by using this one basically. This inversion is obtained by fixing the slotted plate. So this all slotted plate. So this is fixed, so it's not moving. The fixed plate or link 4 has two straight grooves cut in it. So when it says two straight grooves, so one of this groove actually and one of this groove at right angles to each other. The link 1 and 3 are known as slider. So link 1, which is a slider B, link 3, which is a slider, which is also slider A. From sliding pairs with link 4, the link AB, so the rod AB is a bar which forms turning pair with link 1 and 3 as it is as discussed already. So when the links 1 and 3 slide along their respective grooves, any point on the link 2, such as P, traces out an ellipse. So this point P on this bar, it will trace out a form of ellipse basically. So you can imagine when it's moving down, this going this way, this. So let's say this is moving down the way arrow shows. So this will go this way. So during this movement, you will get the ellipse actually. The interesting thing is not necessary that this P point could be here. This P point could be here as well. So if I, let's say, if I extend this part and any of this part, you can make P point. So of course, then the size of the ellipse will be different. A little consideration will show that AP and BP. So AP and BP are the semi major axis and semi minor axis. You know that in a form of ellipse, basically, you got one as a minor axis, one as a major axis. So major axis is the longer axis and minor axis is the smaller axis. So this one, this side is a minor axis. And when you have a circle, so basically they are same. So minor and major axis are same, which is equal to the diameter basically. So this can be proved as follows. So we have one of the, yeah, before we go to the proof, I have very short video to play to just show you how it works. So the calculations and proof for the AP and BP will be discussed in the next slide. Just have a quick view of the animation, how it actually works. Uh, so you see, so the P point could be at any side. So P point actually this shows the major axis, uh, which is much larger this time. So you see, it is quite interesting setup where the sliders have to move in their fixed position. So they are just moving in a straight line, you see. So for example, one of the slider, which was slider A, it just moves up and down, and slider B in our drawing is moves right to left only. So the length, the length itself, AP, is basically the double of that one. As I said, the major axis and minor axis would be defined with the length of this bar, which is a green here, basically. One last time I will play. So I took this from YouTube, and where it explains that it is quite useful when you're drawing large ellipses, basically. All right. So we have a short proof, basically. Not a proof, just the explanation of this drawing, basically. So let us take OX and OY as horizontal and vertical axis. So we got here OX. So this OX and OY are considered as horizontal and vertical axis, and the link AB, and let the link BA is inclined. So the link BA, so this is the link BA, is inclined at an angle theta with the horizontal. So basically this AB, which is here, so this AB is forming a link and forming an angle with along with x-axis, for example, as a theta. So we are drawing on the Cartesian coordinates. Now the coordinates of point P on the link BA will be. So we are interested in finding the coordinates of this location P, because that's the one which defines the major and minor axis for the ellipse. So P point is the one which is basically plotting the ellipse. So the x dimension, which is this one from here to here, the x dimension would be, if you look at this one, uh, so if you look at this triangle, little triangle, this one, because if this angle is theta, so this angle is theta as well. So x is basically PQ. So PQ is this length, which is the cosine of AP. So you can imagine this is a triangle, so it's hypotenuse. So if this is hypotenuse AP, so PQ is a cos component and AQ is a sine component. That's what we're saying. AP, so x is equal to AP cos theta. So this one is AP cos theta, basically. AP cos theta, right? And the second one, we are interested in the dimension y, basically, because y is this one. So you see, Yeah, before that you actually need to see what are x and y. So this is y, so this is also indicated. So for to evaluate y, now this time we are doing this little triangle, this one, right? So here in this triangle, if I make it like bigger triangle, so we got this angle theta, and this is P, this is B, and then we can work out. So if this is PB, you can basically find the sine component. So this is Y should be sine component, and along with length BP. So this is the length basically. This one, that's why. So you can rearrange this equation. X over AP will be cos theta, and you can bring this BP over there. So this is sine theta. So you just want to write in terms of cos and sine, just because we want to relate with the angle. So now we got two equations for X and the other one for Y. So now what you do, you square and add both together. So you square both sides. So X square over AP square, so this side, and Y square over BP square, so this side. And then the right hand side would be cos square theta and sine square theta. And this is very famous equation for a circle. Trigonometric relation, cos square theta plus sine square theta is 1. So that's, you see, this is one of the equation for an ellipse. This is a famous equation. So x, if I write it like this, so x over a, uh, so x square over a square, y square over b square is equal to 1. So that's the famous equation for ellipse, the standard equation where a and b are the major and minor axis basically. So this is the equation of an ellipse. Hence the path traced by the point P is an ellipse whose semi-major axis is AP. So the AP is a major axis and minor axis is BP. So BP, this part, is the minor axis. If you look at this one, so the BP is a minor axis. So if P is the midpoint, let's say what you have, this P point is somewhere in the middle. So AP and BP are same. So AP and BP are same. So what happens? So you can rearrange this equation now. So if P is a midpoint link BA, then AP is equal to BP. The above equation can be written as, so let's say x square over AP square. Instead of BP square, you write AP square because both are same. So then of course you can take common and bring it over here. So this is, so now you see this equation is basically a circle equation, and x square plus y square is equal to r square. So AP is a r now here. So this is the equation of circle whose radius is AP. Hence P is a midpoint of link BA, it will trace. Yeah. So you see this elliptical trammels, which are mainly being designed to draw ellipse, can also be used to find the radius. So draw the radius, the circle as well, basically. All right, so this is one of the double strider crank chain elliptical trammels. Then we have a Scotch yoke mechanism. This is also quite interesting actually. So what is it? So in Scotch yoke mechanism, so it's right literally. So in Scotch yoke mechanism, this mechanism is used for converting rotary motion into a reciprocating motion. The inversion is obtained by fixing either the link 1 or link 3. So either you can fix link 1, which is this one, or else you can fix link 3 as well. So in figure, link corresponds to crack. So that's this link 2. So this is link 2 basically. Link 2 corresponds to crank, rotates about B as a center. So in this particular example, so this rotates around B. The link 4 which corresponds to frame. So this all is frame. This one is frame. The fixed link 1 guides the frame. So link 1, the fixed link 1 basically is uh, guiding the frame as well, basically guiding. Yeah, so it's a guides on a frame basically. So I think this animation will be more easier to understand. Yeah, so as I said, this yellow part is a crank which rotates around a fixed center, which is this one B, when it's moving. So then the slider link 3, which is like the blue, it helps to provide the guideway. So it's moving up and down basically. And this is helping to get the reciprocation on of the blue bar basically, which is basically is also shown over here, which is like a piston assembly. So now you can imagine this can be of both category. So let's say this one, you can rotate the crank. So when you rotate the crank, you have the reciprocation here. But in case you have the reciprocation here, you can rotate here. So the crank. So it could be other way in any direction basically. Yeah. Then a very interesting mechanism, which is a double slider crank chain inversion, Oldham coupling. This is very interesting, basically inversion. So Oldham coupling is used for connecting two parallel shafts whose axes are at small distance apart. So you see, this is one of the very big challenge in some of the geometries, if you think about it, because the shaft process, where the shaft is required from driver to driven, right? So we have the energy source as the driver, and then we have the driven. So the energy has to transfer. But the problem is the shaft has to be in a same axis. But because of different complexity in engineering equipments, it is likely likely that the shaft axis could be not in a same axis. So they are kind of like in different axes. So then the shaft cannot be really used because shaft need to be a straight line axis. And yeah, as I said, because if let's say you have a fertilizer plant or oil refinery, so there are different equipments which are required or which has restrictions to be placed at different positions, and they are not in a straight line, then such couplings would be very, very useful. So that's why it is very interesting equipment, uh, or basically the mechanism. Right, so the shafts are coupled in such a way that if one shaft rotates, the other shaft also rotates at the same speed. So of course, when driver to driven, we want it to transfer energy. Uh, so one shaft is rotating, the other shaft has to rotate on the same speed. This inversion is obtained by fixing the link 2. So within this one, we got link to the supporting frame. So all this is basically linked to this one and this one. So we fix it. So link 2 is fixed. The shaft to be connected have two flanges, link 1 and 3. So the driving, so within this geometry, we have one driving shaft and this is driven shaft. So basically we are transferring energy from this shaft to A shaft to B basically. And each shaft has a flange. So this has a flange. So this is one of the flange. which is connected to the driver. Now we got another flange. So we got driver, which has this flange basically. Sorry, driven. So driven has this flange, which is connected with the shaft rigidly. So this is connected rigidly, or it could be part of the shaft, but they are more likely, the flanges are connected with the shaft through one of the key, for example. So they're connected like that. Fastened at their ends by forging. So forging is also a process you can. It depends on the type of coupling you need to do basically. So now link one. So link 1 and 3 form turning pair. So link 1, which is the flange A, and link 3. So this link 1 with this flange and this flange, both flanges are basically are making a turning pairs with link 2, right? What is link 2 now? So link 2 is basically the frame as discussed. These flanges have a diametrical slots cut in their inner faces. So within each link we got the link cut basically. So this is, for example, so we are talking about link 1 flange, which is connected with the driving shaft. So this is the link 1, and it has this slot cut in it basically. Yeah, so that's the slot cut in link 1 basically. The intermediate piece, link 4, which is this one, link 4, which is the intermediate piece between both flanges. You see this one, we are talking about this one. So this one basically is this is the intermediate piece basically, which is circular disc have two tongues. So it is protrude. So this is the intermediate. This is the link 4. So it has two protrudes at 90 degrees. So one is this protrude is writing as a tongue basically. It's just outside of the geometry. One this side, one that way, one this way, and one that way basically. The tongues on the link 4 closely fit into the slot in the two flanges, link 1 and 3, and link 4 can slide or reciprocate in the slot in the flanges. So link 4, this one can sits nicely within the link within both flanges basically. The intermediate piece can fit within the two sides basically. So when the driving shaft A is rotated, the flange C, the link causes the intermediate piece link 1 to rotate at the same angle through which the flange has to rotate. Now, the working cycle basically. So the shaft has to rotate. When it's rotating, of course, the flange, which is rigidly fastened, it will also rotate. When this one rotates, this also helps to rotate the intermediate piece at the same speed. So it just further rotates the flange D, and now once it's rotating, the flange has rotated, and it further rotates the flange D uh, velocity at very instant. So when this intermediate piece, it also helps the flange 3 to move as well. A little consideration will show that there is a sliding motion between link 4 and each of the link 1 and 3. So the intermediate piece is basically sliding within the slots continually when it's moving. So the intermediate link is sliding basically within each flange. I think I will have one of the animation. Yeah. So we can look at this one. So you see when it's moving, you see how the intermediate piece is nicely sliding against each other. So it is quite interesting. So you see driving shaft is here is a let's say at this one, and the driven shaft is a little bit up, so they're not in the same axis. So now this angle shows very nice movement. So the intermediate piece keeps sliding within the flanges. So this design is in such the intermediate piece is brought back to the original position by this continuing movement by itself. So you have continually sliding intermediate piece. Yeah, so this angle shows a little bit better overview. And also interestingly, both the central part, the coupling actually is of same size. And of course, when it's moving, it depending on the axis difference, this would come out of the central position, but it will do basically the job. All right. Then we have some of the problems which would yeah, so these examples, some of these examples already discussed, and there are few problems are given here just for your practice. Um, so for convenience, I have also included the answers, so you can just cross-check your answer. And these problems are those problems which are already discussed within the same uh, presentation. So we have done some inversions for 4-bar link, and within that inversions we have solved some of the examples, and the problems are also of similar topic. So you will not face any difficulty. Uh, so, but of course, if let's say you struggle with any question, we can go over that. So we have one of the assigned problem 1, and this is 2. This is with the crank and slaughter lever quick return mechanism. This is also crank and slaughter lever quick return mechanism, and where you need to work out the time ratio. And here is also determine the time ratio and the time ratio as well, basically. And this is another problem for crank and slaughter lever quick return mechanism. So the examples from 5.1, 5.2, 5.3, the one we have done, those were for crank and slotted lever quick return mechanism. So you shouldn't have any problem with that. And then 4 and 5. So this one, these two are basically Whitworth quick return mechanism. So we have solved one of the problem. So here you might need a little bit of drawing as well. So yeah, I'm quite sure you will be able to do it. Just make sure you do it rightly, basically. So this is fourth problem, and the fifth problem is also same, where some of extra information is also given, like length of stroke and driving stroke length and other parameters. So you need to work on those things. All right, so these are 5 problems are being assigned to you. So I leave them to you. So you just do it. Do your best to attempt. But of course, if you struggle with anything, we can discuss. And I think one of the problem, which is most probably the 5th one, is also part of your CEP, which is supposed to be submitted by early in the first week of next month, basically.
All right, so that's it. So we'll continue with the next topic afterwards. Allah Hafiz.